So rotational motion. What have we learned so far? Let's review it. Okay. We said if I have an object rotating around some fixed axis, so basically any object which can rotate around a pivot point, what I can do is define an angle as my rotational position. If I take a derivative of that angle with respect to time, I'll find angular velocity. And if I take a second derivative, which is d omega dt, is going to be alpha of t. It's angular acceleration. In terms of linear motion, these were like x, v, and a. So basically anything we have derived for x, v, and a, we could actually apply to theta, omega, and alpha. Now, how about dynamics? Kinematics was simple, just as we did in 1D motion, we can do it for the rotational quantities. For dynamics, we said instead of force, I'll have torque, just as F was equal to ma, torque was equal to I times alpha. So this was torque. And how was it defined? Torque was defined as R cross F, where if I had some object, the distance from the pivot point to the application of the force gave me the R vector, force gave me the other vector. So R cross F told me how much torque is applied onto the system. Alpha was angular acceleration, and I was moment of inertia. How was it defined? It basically acts like mass for rotational quantities. This equation is equivalent to F equals ma in linear motion. Moment of inertia we have defined as I was integral r square dm. For a few objects, we already calculated it. We had a list. We said if I have a ring of radius r and mass m, I ring through the center was m r square. If I had a disk of mass m and radius r, I disk was m r square over 2. If I had a uniform rod of length L and mass m, I rod was m L square over 12. And why did I just tell you the moments of inertia for only the axis passing through the center of mass? Because we had this very useful theorem. What was it? It was called the parallel axis theorem. Said that moment of inertia for any axis which is a distance d away from the center of mass is equal to I center of mass plus total mass times d square. Now, we've solved a few problems where we needed to calculate the moment of inertia. We've also solved a few problems where we used torque equals I alpha in combination with F equals ma, right? So we had these pulleys and masses. Pulley was rotating, masses were moving linearly, right? So let me go ahead and discuss kinetic energy of rotation. Now, what do you think would be the kinetic energy of an object rotating with angular velocity omega? Kinetic energy for linear motion was 1/2 mv square. Then kinetic energy of rotation would be 1/2. Instead of m, I would have I. Instead of v, I would have omega I omega square. Okay? Now, but we have to be careful about which I and which omega. It's just a cryptic comment I make so that you stay awake. Okay, be careful, do not go to sleep yet. We'll have some surprises coming. Now let's solve one example. Okay, let's say that I have a pulley. So this is a disk of mass m and radius r, and onto that I add a mass small m. And initially this mass m is a height h above the ground. The question is, how fast does m hit the floor if it starts from the rest configuration shown? Now, let me solve it two ways. Okay. What's the conserved quantity during this evolution? I mean, first of all, what do I expect the system to do? There is a mass, there is a pulley. The mass is going to fall down. As it falls down, there is a string, so the pulley will rotate, right? So, what's my guiding principle here? Which quantity is conserved? Energy is conserved. I cannot talk about momentum conservation. So energy is conserved. In the initial configuration, this is m, this is m, r. Let me choose my reference level to be the ground level. Can you tell me what's the initial energy? Is there any kinetic energy? There is no kinetic energy, so it must all be gravitational potential energy. Now, this is h. So the gravitational potential energy coming from small m is mg h. How about the capital M? How about the big pulley? Now, here is something that's really important. I've said this only once throughout the lectures. This is a good time to emphasize it. If I have an extended object under gravity, what is its gravitational potential energy? Should I take the bottom point, should I take the top point or should I take the center of mass as my height from the ground? Okay, I've said this once. Let me repeat it again. It's going to be, let's call this HCOM. So there will be, although it's not going to matter in this problem. Oh, come on. MGHCOM. Potential energy depends on the position of center of mass. Okay, so that quantity center of mass is really useful. How about in the final situation? What happens in the final situation? I have a disk now. And mass m is hitting the floor with some velocity v. But that means my pulley is also rotating with some angular frequency, omega, right? So can you tell me what the final energy is? Let's write the potential, gravitational potential energy first. What's the gravitational potential energy coming from small m? It's 0. It already hit the floor. How about the large m? It's again going to be m times g times h center of mass. But now I have kinetic energy, and I have two types of kinetic energy. First is 1/2 small m v squared. That's the kinetic energy of the mass moving with velocity v, small m moving with velocity v. But I should not forget the energy, the kinetic energy of rotation of the pulley. So for that I have to also add 1/2 I omega square. And I for the disk was mr square over 2. So this is mghcom plus 1/2 m v square plus 1/4 m r square omega square. So now I can write my energy conservation. EI is equal to EF. EI is mg HCOM plus mgh is mg HCOM plus 1/2 m v square plus 1/4 capital M r square omega square. Hey, I have two unknowns, v and omega, but I have only one equation. So I need to find one more equation. Now, where would that equation come from? Is the speed of this small m somehow related to the rotation speed of the pulley? It must be, because they are tied by the same string, right? So if, well, my computer is acting up today. I hope it doesn't crash. So if this thing rotates by theta, it's going to go down by r times theta, right? The string that's left by the pulley would be added to the length of the string carrying small mass. So d theta dt is omega d by dt r times theta is v. Or in other words, omega is, or r times omega is v. Okay. So that is the condition that's actually constraining v and omega. is that clear? That's you're going to have to use this condition over and over again. Okay, we'll talk more about that. But do you understand why the rotation velocity, angular velocity of the pulley actually determines the velocity of the small mass? Well, it's very simple, right? The string is being unwound from the pulley as it rotates, and that string actually is added to the distance from the pulley to the small mass, right? That's why V and omega are related. If I had some sort of not a string, but some spring or stretchable string between these two objects, then these two would not be related. Good. So now I can actually use, so this is my first equation. My second equation is that omega times r is V. Maybe another way to think about it is, what's the velocity of this point at the, it's omega r, right? At the tip of the, at the edge of the pulley, V is omega times r, and the velocity of that point is exactly velocity of the small mass. Okay? Maybe that's easier to grasp. Good. So now I can actually do that. I can plug that second equation into my energy conservation. mgh is 1/2 m v square plus 1/4 m. Omega is v over r, so r omega is actually v. V square. So maybe I can write all of this as mgh is 1/2 m plus capital M over 2 times v square. So v is 2 mgh divided by small m plus capital M over 2 square root. That's the answer I'm looking for, right? Any questions? Yes?
Can we say the rotational motion is provided by the
Friction?
friction?
I don't see where the friction comes into play.
No, in work energy, using work energy term, we don't use friction as.
So, I think, so maybe you're basically asking me if this, why is that rope making the pulley turn, right? That's, I think, well, I wasn't really thinking about the mechanism which ties the string.
No, when we use work energy theorem, do we include frictional work?
Oh, here I don't think there's any friction in the problem anywhere, right? And if you're talking about air friction, I totally neglected that.
Not air friction. Friction on the pulley and the string.
Okay, so good. Now, the pulley, the string that's tying the center of mass to the ceiling is not moving at all. There is no friction there, right? So you're basically worried about the rope that's wound around the pulley, right? And I thought maybe the end of that rope is actually attached to somewhere on the pulley, so it makes actually it turn by a force. But it could just as well be because of the friction between the rope and the pulley, but that's going to be static friction. And static friction, as we're going to see later today, does not dissipate energy. Okay? It's actually a good question. It took me a while to understand it, but that's a good question. Any other questions? No? Let me solve it another way. Let me solve the same problem in another way. So solution. You may say, hey, energy conservation is hard. Well, it's not, but let's say that it's hard. But I know one thing very well. I know how to solve my dynamical equations well. Okay. So what I'll do is I'll actually draw free body diagrams for both objects. For the small mass, I have mg pulling it down and t pulling it up. For the pulley, I have t acting on the edge and some, let's call this T2, and its weight mg. Now, let's say that this guy is moving down with A and pulley is rotating with alpha. Now, what's Newton's equation for the small mass? M times A will be mg minus t. How about F equals ma for the pulley? Well, I'm not interested in that, right? There is this string that's tying it to the ceiling, so it's not going to move. So F equals ma doesn't give me more information. It tells me the value of T2, the tension in the string pulley, connecting the pulley to the ceiling. But I have one more equation when I have an extended object. What's that? It's the rotational dynamical equation. I need to apply torque equals I times alpha. So what is the torque in this case? This is R, this is 90 degrees. So torque is, the magnitude of the torque is T times R. So I times alpha, if alpha is this way, is T times R. And I know to be mr squared over 2 is T times alpha. But again, I have two equations and I have three unknowns, T, alpha, and A. So I need at least one more equation. Where would that come from? Again, the acceleration of the mass going down and the angular acceleration of the pulley are related. Which way are they related? If I just take one more derivative of this relation, I would find alpha times R is A, right? So I can write this alpha times R is A. That's great. So that's my third equation. I can write this as m A over 2 is exactly equal to T. And now I can plug this guy over here. I'll have m small m A is mg minus m over 2 A, or A is m divided by small m plus capital M over 2 times g. I found acceleration, but what did the question ask me? It asked me to find the velocity when it hits the floor. So this is my acceleration. Can you tell me how long will it take for m to hit the floor? Well, this is motion with constant acceleration. So 1/2 A, let's call this Tf squared, would be h. So in other words, Tf would be square root of 2h over A. Then what would my final velocity be? It will be A times Tf, right? That's motion with constant acceleration. Or in other words, it will be 2h times A. Now I can plug in what A is. I find, oh, 2 m h g divided by m plus capital M over 2. 2 m h g divided by small m plus capital M over 2. So we found the same result. Okay? Which probably means it's correct. I'll not even bother to check the units. Now, which one is easier? Energy conservation or dynamical equations? Energy conservation is easier. But did we do all the second calculation for nothing? No, actually we have obtained something that we did not find in the energy conservation equations. We obtained how long it would take for this object to hit the floor. So that's another piece of information we obtained because we solved the dynamical equations. Good. Let's solve one more example. Let's say that I have a rod of length L and mass M, which is a uniform rod. And I fix it from its end point. Right? So essentially the rod is at rest like this. If I let the rod go, it's going to swing. It's going to swing down. So what I would like to find out is when it swings down, what's the velocity of the center of mass as it becomes exactly vertical? Okay. Find VCOM as rod passes through vertical configuration. How are we going to do this? Yes. Louder, please. I could not hear you. Yes, we can use energy conservation. I know it's almost 9 a.m. in the morning and it's still dark outside, but try to be more lively. You know, your exam will start at 9, right? On Saturday, so you should 10? Yeah, I don't know. Okay, I just made that up, but you should wake up in any case. Okay. Good. Now, energy conservation. So here's what I'll do. I'll choose. So the solution is energy by energy conservation. So I'll choose my reference level to be the initial configuration of my rod. What's the energy in the initial case? Mom, I chose my reference level to be exactly at the rod's place. So is there any potential energy? There is no potential energy. Is there any kinetic energy? Nothing is moving. Initial energy is equal to 0. Can energy be 0? Yes, of course. I mean, why not? Okay. But that's what a lot of students do. You know, I see solutions where someone finds energy to be 0 or negative, and he or she just gives up. Oh, I found negative energy. That must be wrong. No, that's nice. you can have negative energy. Apparently, my total energy is 0. So let's see. How about in the final configuration? In the final configuration, what's my potential energy? Potential energy was controlled by the height of the center of mass. It's going to be m times g times center of mass is L over 2 below the reference level. So it's going to be minus mg L over 2. Okay, I'm below the reference level. How about the kinetic part? Well, this is rotating with some omega, so it must be 1/2 I edge times omega square. Okay. Let me do my solution, and then energy initial is equal to energy final. Energy initial is 0. Final energy is minus mg L over 2 plus 1/2 I edge times omega square. And I remember the following. Around the center of mass, my moment of inertia for a uniform rod of length L was mL square over 12. So I don't know what's up with my computer today. So around the edge, what's it going to be? It's going to be I center of mass plus m times the distance, which is L over 2 square. So L square over 4. So it's going to be m L square over 3. I'll pass the first term to the other side. M G L over 2 is 1 over 2 m L square over 3 times omega squared. 1/2 cancel, m's cancel, 1 power of L cancels. 3g over L square root is omega. But that was not what was asked. I was asked to find V center of mass. What's V center of mass? If this thing is rotating with omega, V center of mass is omega times the radius, the distance from the pivot point, which is L over 2. So it must be omega times L over 2, right? So V center of mass is omega times L over 2. So it's going to be square root of 3g over L times L square over 4. L's cancel. So it's going to be square root of 3/4 GL. Question?
Why is there only rotation of kinetic energy?
Excellent question. That's exactly what I want to talk about. The center of mass was moving with some velocity. Why did I not include the translational kinetic energy of this object? Okay. So, and this is an important point. Now, in general, if I have an object like this, you ask the question, you catch it, I'm going to throw it. It did two things. It was being translated, and it was also rotating, right? So in general, if an object is moving, it's going to have two kinds of motion. Motion, motion kinetic energy due to rotation, plus kinetic energy of translation. Okay. Now, total kinetic energy is going to be 1/2 m, that's the total mass, times v center of mass square, plus 1/2 I center of mass times omega square. And that only works for center of mass. You cannot in general say, hey, let me look at the edge of this object. The total kinetic energy of the system is 1/2 times m times v edge times 1/2 I h times omega square. That would be wrong. This formula only works for center of mass. Okay. In this problem, then I did something which is kind of, it looks kind of strange. Okay. So let me solve this problem once again. I'm going to solve it once again using this prescription. Okay. I'll say my initial energy was 0, and as it actually passes through, here there is VCOM. My final energy is minus mgl over 2, that's my potential, plus 1/2 m times v center of mass square, plus 1/2 I center of mass times omega square. Okay, but now omega is clearly v center of mass divided by L over 2. So that is also equal to E initial, which is 0. So mg L over 2 is 1/2 m v center of mass square plus 1/2 m L square over 12 times v center of mass square divided by L square over 4. Okay, I'm basically writing omega in here. So m's cancel everywhere. 1/2's cancel everywhere. GL is v center of mass square. 1 plus L squares cancelled here. 1 plus 1/3. Or v center of mass is square root of 3/4 GL. Hey, I found the same result. So now comes our simple rule. Writing the kinetic energy is as 1/2 m v center of mass square plus 1/2 I center of mass omega square is always correct. But if your object is rotating around a fixed point, it's not doing both translation and rotation. If it's not free to move, it's actually fixed in space by a pin, by a needle to some point, then I can write kinetic energy as 1/2 I pivot, so around this point basically, times omega square, and in that case I will not actually use any kinetic energy of translation. Okay, if my object is fixed to the floor, if you want, from its one point, that's pure rotation around that point. So I don't actually have translation. But the first formula is always correct, whether you're fixed to a point or whether you're actually moving in free space. All right. So my advice to you is, when you're writing the kinetic energy of an object, always stick with the center of mass coordinates. Yes?
Equation is always correct. So why we use IP?
Well, sometimes it's easier. Okay, that's why. I mean, in the previous case, look at my solution. It's one step easier, right? So it's one step. There's only one term here. There are not two terms. So that's why. You should know both. Yes.
In the second case, we don't use the parallel axis.
In the second case, I pivot is actually determined by the parallel axis theorem. Oh yes, yes. I explicitly write ICOM. Okay, it's only, it has to be the center of mass, moment of inertia.
So in the first case, we are just integrating using parallel axis theorem. We're just writing those two equations.
Yes. So these two equations are both correct because of parallel axis theorem. If you want, you can go from one equation to the other using parallel axis theorem. That's a good observation. Now comes something more. Let's talk about rolling. Why do you think the invention of the wheel was a big deal? Why do you think wheel was important? That's a rhetorical question. I'm not asking for answers because you all know the answer. It's actually easier to move things with wheels. But now we must ask, why is moving a wheel easier? I mean, if I just look at Newton's laws, I mean, if I had no friction anywhere, moving a wheel would not be easier than moving a block, a cube, right? But the nice thing about this circular geometry of the wheel, and my circle looks terrible, and I need a good circle now. So I'll actually, okay. Now, what happens when I'm rolling a wheel on a surface? So rolling a wheel on a surface means, it's very strange. My pen is stuck. When I'm rolling with omega, all the points on my wheel are mapped one-to-one to points on the surface, right? That's what rolling means. And in that case, if I roll the wheel by an angle theta, so now what happens is that after I roll, right? If this was the first radius, that becomes the first radius. How much did my object move by? If that's r, it has moved by r times theta, right? So in that case, can I talk about the velocity of this object compared to the angular velocity of rolling, velocity of rotation? Yes. Again, taking a derivative, I can say velocity is omega times r. That's rolling condition. And here is something surprising. During rolling, there may be friction, but it does not dissipate energy. Seemingly contradictory statements. Let me again draw a nice line and also a nice circle. Now, if I fix one point on the circle and look at its motion as this circle rolls on my surface, I'll see an interesting curve. The curve is such that that point sort of basically touches the surface and comes back again. And I could not really draw it very well, but it comes to the surface perpendicularly. Okay. When I'm exactly at the rolling condition. So if I'm actually an atom sitting on the surface, okay, I do not see something sliding above me. What I see is some other atoms come to me head on, collide with me and go back. So I cannot really act friction, or I cannot really dissipate energy. There may be a force between these two surfaces, but there is no displacement with respect to each other. So no displacement, no dissipated energy. So what does that mean? Basically what I'm saying is that if I take a nice marble, children's toy, a ball, if I actually roll it so that its velocity is omega times r, it will actually keep rolling without losing its velocity. It will keep rolling to infinity. First of all, obviously that's not correct, right? It will not roll all the way to infinity. However, we also know by experience that it's going to roll for a long time. The more circular, the more perfect your sphere is, the more it's going to keep rolling. Actually, the only way a rolling object dissipates energy is because it's not a perfect sphere or the floor is a perfect line. Okay. In general, when you put an object, a spherical object, onto the surface, it's going to sag a little bit, right? There will be a finite region of contact. If there is a finite region of contact, all the points except the minimum point dissipate energy. They move with respect to the surface. So there will be energy dissipation. That's why actually if you have your tires underinflated, they are not fully inflated, they will look like this when they are on the floor, right? There will be a flat region. They are going to dissipate more energy. It will be harder to ride your bike with underinflated tires because you're actually losing some energy to the friction. Okay? So rolling objects stop because they are not perfect circles. So let me state one problem. Let's say I have a sphere of radius r and I is 2/5 mr square, I would like to find out it rolls down this inclined plane of angle theta from a height h. I would like to find out what's its final angular velocity and final velocity if it rolls without slipping. So 10-minute break. When we come back, we'll discuss what happens in this problem.